Yesterday we started chapter 7 and we started in section 1. We started talking about inverse variation, which inverse variation always looks like y equals k over x. The variables x and y might change depending on the context of a problem to represent something, but it always sort of has that very simple form, y equals k divided by x, which is really like y equals a number divided by x. Today what we're going to do is we're going to skip over section 7.2. We're going to come back to it, but we're going to do it at the end of the chapter. And this is graphing rational functions. And actually there are some really helpful things that we can get that will help us graph rational functions if we do some of the algebra stuff before we do that. So we're going to skip ahead to section 7.3, and we're going to start talking about simplifying, multiplying, and dividing with rational expressions. So we'll talk about what is a rational expression, and then we'll look at some old examples, and then we'll look at some new examples from Algebra 2. So first thing we want to do is talk about what do I mean when I say you're going to simplify, add, and subtract rational expressions. Okay. Well, rational expressions have a math word in them, and that word is ratio. So anytime I see the word rational, I instantly think ratio. And what do you guys think about when you hear the word ratio? What is a ratio, or what does a ratio look like? Oh, when you multiply two fractions? Could be, yeah. What else do you think about when you see a ratio or hear ratio?
I don't really know, so it's like, it would be like 4 and
Yeah, so like fractions and colons are usually the way that we see ratios. Now, I'll say a single ratio really only needs to be one fraction. So, Jackson, you talked about multiplying fractions, which is what we're going to do today. So those are multiplying rational expressions. But a rational expression all by itself, a ratio is just a single fraction. And all fractions have numerators and denominators, and the fraction bar represents division.
Ninth grade students with the last name starting with letter K. Ninth grade students, last name starting with the letter K to the health office.
So since the fraction bar is really division, all fractions are really just quotients, which makes sense. If you think about the fraction 3 over 4, it is just a quotient, which comes out to be 0.75 if we do the work. Okay, so fractions represent quotients. Okay. Now, what we're going to work for today is to make sure that all of our rational expressions are written in what we consider to be the simplest form. So my question to you is, and you learned this way back when in grade school, how do you know when a fraction is in its simplest form? Bailey? It can't be reduced any more than it is. So simplest form from long ago is when your numerator and your denominator have no common factors. When your numerator and your denominator have no common factors. So like Bailey said, it can't be reduced anymore. An example from elementary school could be a numerical fraction like 6 over 10. Is 6 over 10 in its simplest form? Certainly not. You guys would tell me to do what? Yeah, divide by 2 in the numerator and the denominator and turn it into 3/5. Okay, absolutely. I'm going to show you like the strategy that we're going to use today, which is going to involve factoring things. So if we factored 6 using the factor tree, we would think about, okay, what numbers multiply to give us 6? 2 and 3, right? And then it's in its simplest form. So I could rewrite 6 as 2 times 3, and I could rewrite 10 as 2 times 5. And those are like their prime factors. We can't go any lower than that. And you guys were saying, Kyle said, divide by 2 at the top and the bottom and make it 3/5. Here we can clearly see why we should divide by 2, because there's a 2 in both numbers. Okay. And the only reason I'm showing you this is because it looks more like what we're going to do today, which involves factoring. Okay. So we come up with 3/5. Now, you also did some problems in Algebra 1, where you simplified more complex fractions than something like 6/10. So we had problems in Algebra 1 that might look something like 2xy, I'll make it 2x squared, over 8xy to the 4th. And so in Algebra 1 we said, hey, you can simplify things that don't just have numbers. You can simplify things that have numbers and variables and exponents. And so you guys have some like little things that you would use to simplify this. You would say 2/8 is really 1/4. And then for x squared over x, you could subtract your exponents, 2 minus 1, and you'd have an x left over in the numerator. And for the y's, you could subtract your exponents here. Y to the 4th minus 1 would be a y to the 3rd in the denominator, because there's more y's down there. I'm going to show you what we would do today. What we would do is we'd write this out as all the different factors. So all the different things that multiply out in the numerator and the denominator. So like 2x squared y could really be written as 2 times x times x times y. And I would guess most of you don't need to do this because you have those exponent properties from Algebra 1. And in the denominator, I could even rewrite 8 just like I did with 6 and 10. If I do a factor tree for 8, that's 4 and 2, 2 and 2. So 8 is really 3 2's multiplied together. 2 times 2 times 2. And then I'd have times x times y times y times y. I'm doing way more work than we would normally do, right? But what I'm showing here is if I write out all the factors in the numerator and write out all the factors in the denominator, then I can do just like I did before, and I can say, well, cancel out a 2 in the top and the bottom. I'll cancel out an x in the top and the bottom. And I'll cancel out a y in the top and the bottom. And then I'll just write whatever's left over up in the numerator. I'd have x. And in the denominator, I'd have 2 times 2, which is 4, and y times, ooh, I forgot a y down there, didn't I? Y times y times y, which is y cubed. Which, this is the same answer you'd get by reducing 2/8 and subtracting your exponents. And you'd be left with 1x in the numerator and 4y cubed in the denominator. We're going to focus on this idea of factoring the numerator and the denominator because that's going to be really important for what we are doing today with our rational expressions. They look even more complicated than what we saw in Algebra 1. Okay, so here's our first example of what we're going to do. Let me give you the rational expression x squared plus 5x plus 6 over x cubed plus 2x squared. Now I'm going to demonstrate the wrong thing to do, the trap I do not want you to fall into. Do not write this in your notebook. We will do it correctly in just a moment. Okay. This is something that I call getting cancel happy. Okay? And this happens when people don't do any homework all chapter and then they show up to my quiz or test. Okay? And they don't do any preparation. They get to something like this and they say, oh, simplify this. Okay, x squared cancels with x squared. 2 and 6, I'll make that 3. And some people might say, oh, I'll cancel an x and an x. And just go around canceling whatever the heck I want, wherever I want. That is cancel happy. Do not call credit to being cancel happy. Okay? This is wrong. The reason why this is wrong is these separate things in the numerator and denominator are not factors. Like x squared is not a factor in the numerator. And x squared is not a factor in the denominator. In math, we call those terms. They're terms because they're things that are getting added or subtracted with other terms. Okay? So you're never allowed to just cancel just 1 or 2 terms and not all the other terms. It's illegal in math. So what you have to do is you have to rewrite the numerator and denominator so that instead of seeing terms, you see factors. And that's why step 1 of simplifying rational expressions today is factor everything. And when I say factor everything, I mean factor the numerator, factor the denominator, factor everything possible. So up in the numerator, I've got a trinomial. Thinking back to factoring, trinomials will factor into 2 binomials. I think about that very first term, which is x squared. What must multiply to give me that x squared at the first term? X times x. And then I always go to the back of the trinomial. What are factors of 6, positive 6, that add to make 5? 2 and 3. And it needs to be positive 5, so they'll both be positive. Plus 2, plus 3. Some of us will have to spend a little bit more time in Chapter 7 reviewing our factoring skills, and others of us will be ready to kind of fly through. Okay, but factoring is going to be really important from here on out. In the denominator, I don't have 3 terms. I only have 2 terms. What I might check here is, do they have anything in common? X cubed and 2x squared. Well, they both have x squared. So I can cancel, or not cancel, I can factor out an x squared from both terms. I can pull that x squared out and then write whatever's left over for the 2 terms. That would be x plus 2. So step 1, make it factored. So now instead of having terms in the numerator and denominator, I now have factors. Things are getting multiplied in the numerator and things that are getting multiplied in the denominator. If you have things that are getting multiplied in the numerator and the denominator, then you can look for things that are the same and cancel them out. Okay, so step 2, after you factor everything, cancel out common factors in your numerator and denominator. So in this particular problem, we could cancel x plus 2. X plus 2 is a factor in the numerator and a factor in the denominator, and Bailey said it's not in simplified form if it can be reduced, so we cancel it.
9th grade students with the last name starting with the letter L to the health office. 9th grade students, last name starting with L, please report to the health office.
So I get x plus 3 over x squared. Now again, you have to resist the urges to get cancel happy. You cannot cancel those x's because the x in the numerator has a plus behind it. So it's a term, not a factor. Do not cancel it. Any questions about what I just did? Why I just did it, how I just did it, where something went? example that we're going to look at is an example of multiplication. Okay, so I'm going to jump ahead here, and we're going to multiply rational expressions. Notice my two steps for multiplying rational expressions. Do they look familiar? Yeah, they're the same directions for simplifying. Okay. So, something to make note of. Simplifying and multiplying rational expressions are really the same thing. I do have a typo here. Just remembered. This 3 doesn't need to be there. So don't write that 3. Otherwise it won't factor. So on this particular example, I think this is a great one to put in your notes because I'm going to review a couple of special factor circumstances. One of them being that 4-term polynomial in the numerator and how we go about factoring those things. Okay, well, I'm going to factor the hardest part first. Okay, which is this long polynomial. I'm going to give myself a little bit of space down here. X cubed plus 3x squared minus x minus 3. To factor things that have 4 terms, we use a method called factor by grouping, which means group the first 2 terms together, group the last 2 terms together. So I use parentheses to group. So I'm going to put the first 2 terms in a group, and I'm going to put the last 2 terms in a group. Now, this is not factors. What I have to do is next I ignore the last 2 terms. And so I focus only on the first 2, x cubed plus 3x squared, and I just factor out a greatest common factor from those 2 terms. So what do they have in common? X squared. So we'll take out an x squared from both terms, which leaves us with an x plus 3. And then after I factor out the GCF for the first group, then I go to my second group. So I'm ignoring all the stuff in the front now. And I'm only looking at negative x minus 3. And I'm going to ask myself, what can I factor out of those 2 terms? Do they share much in common? No. When they don't share very much in common, that means you're probably going to take out either a positive one or a negative one. Okay, and you always want to put like plus or minus in this next one. What would we want to take out of these 2 terms? Negative 1. So we're going to put a minus 1 right behind it. Make sure you always put plus or minus right there. That's important for your factoring. And then if you factor out a negative 1 from both of those, they'll turn into positives. Faith, did you have a question?
You got x squared and x is x plus 3. I would think that x squared should be 3.
Well, if I think about, so you're questioning this factoring? What I do is always to check if I'm right, I redistribute that x squared. So like x squared times x is x cubed, and x squared times 3 is that the thing that I wanted it to be?
Oh, I
Yeah.
thought you took it from the one.
Oh no, see, I'm doing this one, sorry.
Okay.
I'm doing the big one first. Okay, good. Does anybody remember what we do when we get to this point? For factor by grouping? Kyle?
When you put x squared minus 1, replaces x plus 3.
Yeah, so as long as those 2 groups of parentheses match, that means it was factorable. So we would have x plus 3 as one factor, and then like Kyle said, these numbers that get multiplied in front are our other factor, x squared minus 1. Now notice that x minus, or x plus 3, I only write one time. It's really like that factor had been distributed to the x squared and the negative 1, so it only actually appears once. Okay, it's not a double factor. The last thing I want to do on this, and this is another good review, is factor x squared minus 1. X squared minus 1 is a difference of perfect squares. And so we know, like, difference of perfect squares, if you have a squared minus b squared, it'll factor out into a plus b times a minus b. So this will factor out as x plus 3, and then x squared minus 1 will be x plus 1, x minus 1. If that was x squared minus 25, x plus 5, x minus 5. If that was x squared minus 81, x plus 9, x minus 9. And that's a difference of perfect squares. Now I'm going to take all of this, then, those three factors, and I'm going to sub it in for that numerator. And then we should be able to factor the others. Yeah, most of them won't be that much work. Okay. So I'm going to write right above this. This is x plus 3, x plus 1, x minus 1. Most of your factoring that you're doing in these problems, like on your homework, I know there's one factor by grouping, okay, which is why I wanted to review it. But most of the factoring that you do are either 2-term or 3 terms. And those should be pretty quick for us, okay, depending on our factoring skills. So like in this numerator, x squared minus 2x, each term has an x. So I can factor out x and get x minus 2. In the denominator, x squared plus 2x plus 1. That would be two groups of parentheses, x times x. And then do I have factors of positive 1 that add to make positive 2? Yeah, what multiplies to make 1? 1 and 1. Does it add to make 2? Yeah, so it's plus 1 plus 1. And then on that last one, again, I could just take out an x times x plus 3. And now my last bit of work will be going through and canceling any common factors in the numerator and the denominator. So do you see any factor that shows up in the numerator of one fraction and the denominator of another fraction? If so, shout it out, we'll cross it off. X plus 3. Anything else?
X plus 1.
The x plus 1. And notice, you're allowed to cross out this x plus 1 in the numerator with an x plus 1 in a different fraction as long as it's in the denominator. This is called cross-canceling. And we're allowed to do that. Anything else cancel? The x. There's an x all by itself. Okay, so we'll cancel out x and x. And I think that's it, right? So now you just write what's left over. So my final answer, in the numerator I have x minus 2 times x minus 1 all over x plus 1. You do not have to do any distribution up in the numerator. I don't need that to be written out as x squared minus 3x plus 2. Leave it alone. Move on. Okay. Any questions? Okay, now the next example that I show you, I'm not actually going to work through. I just want to get you to start thinking about things, because the last thing we need to talk about is how to divide rational expressions. So if you saw this from Algebra 1, or if we went as far back as elementary school, 3/4 divided by 1/2. How do you divide fractions? Or how do you divide by a fraction? What's important to remember? Oh, Damon?
You flip the second fraction.
You flip the second fraction. Do you do anything else? You change it to multiplication. I call that multiplying by the reciprocal, okay? And some of you have like a clever way to remember it from middle school. Copy dot flip, keep change, something like that. But it's really called multiplying by the reciprocal. And so the same holds true for us in Algebra 2. Notice that in my steps for division, the only thing you have to do is add step 0. Step 0 is multiply by the reciprocal. Once you change it into multiply by the reciprocal, it's just like multiplying and simplifying. Factor everything and cancel stuff out. So I'm going to give you a little bit of time to just practice your factoring skills. Okay? I would definitely make sure that you multiply by the reciprocal here. So I'll rewrite my work. Or maybe I'll just cross off this one. And then I'll write times. And I'll flip it. I'm going to give you some time to factor, and then I'll put up my factors here in just a little bit, and you can see if we agree. So spend a little bit of time factoring. Call me over if you have a question about factoring. Remember that anything that looks like a trinomial, so it has 3 terms, is probably going to factor out, if it's factorable, to be 2 binomials multiplied together. And we can use that same method as long as the leading coefficient is 1, so it looks like 1x squared. We know that we're going to have x and x for our first terms. And then if it's a 1 for your leading coefficient, it's really easy. Just look at the back number, which is negative 35. Do you have things that multiply to make negative 35, but add to make positive 2? 7 and negative 5, right? Because 7 and negative 5 will make negative 35 when I multiply them, and 7 plus negative 5 will make positive 2. So plus 7 minus 5 would be my factor there. Down in the denominator, again, I have a trinomial, so I'm going to have an x and an x. I have a leading coefficient of 1, so we can use our shortcut here. Do I have factors of positive 12 that add to make negative 7? Negative 4, negative 3. So minus 4, minus 3. In the numerator, 3x squared minus 12x. That does not have 3 terms, so I'm not going to factor it like a trinomial. I'm either going to check for like a difference of perfect squares, like x squared minus 1 was, or I'm going to check to see if they have a greatest common factor. So these two have a greatest common factor of 3x. Thank you, Kyle. And then if we factor out the 3x, we're left with x minus 4. And then we have one more to go. We're going to have an x and an x. Do you have factors of positive 40 that add to make negative 13, negative 8, negative 5? And that will give us a positive 40, but then they'll add to make negative 13. Now I can go through and cancel. Tell me what things will cancel. X minus 5 is good. Thank you, Paul. X minus 4. Anything else? No. Nothing else will cancel. So now we write whatever is left over, which happens to be a 3x and an x plus 7 in the numerator, and an x minus 3 and x minus 8 in the denominator. And again, I don't need you to distribute or multiply that out. This can be your final answer. As long as None of the factors repeat. And don't get counsel happy and start crossing off x's. Okay, that's never okay.